fragmented family, but it is equivalent that pointwise closure of this orbit again the fragmented family. So this looks much stronger because after closure you have a bigger family, but in fact it's the same. In general, you have some fragmented family, pointwise closure will be again fragmented. It's very similar to check it by 3 epsilon argument, like a corresponding property of equicontinuity. Go to the closure of equicontinuous family, you get again equicontinuous family. Okay, the Asplund functions. We use this notation. Of course, if you say Asplund, you may understand now that it's some kind of hint that it somehow comes from Asplund Banach spaces. That's right. That's right. We will see that, for example, for groups, we can consider matrix coefficients, and we can show that every Asplund function on the topological group is exactly are matrix coefficients of Asplund representations. Remember, for example, Fibonacci, in the same way, for example, Rosenthal matrix coefficients. I mentioned Fibonacci sequence and mentioned that the Fibonacci sequence can be represented as a matrix coefficient in Rosenthal Banach space. And now it's the time to understand what does it mean. So we can consider now what is a tame function. We say that, again, it's the same setting. We say that f is tame. We could say also Rosenthal, but it's too much terms around Rosenthal, and tame also is some class of dynamical systems, so it was already occupied. F is tame if, and the notation will be of course, if we have a weaker condition. What kind of weaker condition? If again we have two possibilities. First of all, consider again pointwise closure. Pointwise closure of our orbit. We require that it's eventually fragmented. Okay, what is eventually fragmented? It sounds it's a weaker condition. Okay, let's go to the definition. Okay, yeah, definition 7.7. Oh, no, it's not 7. Yeah. So, what is the eventual fragment? It's a weak version of fragmentability of families. What we require here. We say that our family is eventually fragmented family if for every infinite subfamily we can choose an infinite fragmented subfamily. Of course, instead of infinite we can say also countable and infinite. So it's a much weaker version of fragmentability. It turns out that it captures the difference between Asplund and Rosenthal, between fragmentability and eventual fragmentability. It's this analogy. And for example, you mentioned H+. H+ is a wonderful possibility to understand what's the difference. Just a quick remark, because of course we need to understand if such examples exist. So H plus 0, 1 is some family of functions, homomorphisms from, of course, the family of homomorphisms. In fact, the orientation presently homomorphisms from interval to unit interval into unit interval. Okay? So this family, take it as our original family F. So the remark is eventually fragmented family, but so as expected, yeah, but not fragmented family. In a sense, it will be the reason why the corresponding dynamical system, the action of H plus 0, 1 on the unit interval is Rosenthal representable but not Asplund representable.
So this is just some kind of fact, or is it trivial to prove it? Or?
No, we will touch it in the future. It is absolutely not trivial. No. The second fact is, say, up to my arguments yesterday, not trivial but quite easy. I already explained why this F is not fragmented. You remember butterfly effect argument, yeah? So if you take arbitrarily small some open interval, we can do it bigger, okay? By choosing some element. Because if you take the full family, anyway you can possibility at any time you have possibility to get a large image, large open image, okay? But so this one is say easy. I already gave my arguments by butterfly effect arguments. But the first fact is not trivial. It was open some say 3 years ago. It was open a little bit. Okay. 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 Now say yeah. It's eventually fragmented, and we also say it's equivalent that Fs is equivalent equivalently Fs that will contain an independent subsequence. And what is an independent subsequence? It is a standard definition in Rosenthal theory, so I can show quickly the definition. First of all, go here. Yeah. Independent sequence says, you know, the classical work of Rosenthal. Independent families are independent sequences. Families and sequences play very, very major role. And this definition is standard, well known, not trivial of course, but we have here a possibility to involve this situation. And in fact, this definition of this way to define a tail function is due to Köhler, Angela Köhler. We have a third way to reformulate it. I didn't mention it here. The third way is that is equivalent, is a continuation of this definition, equivalent also the closure P shall F as pointwise closure of our orbit consists of fragmented functions. So if I consider this way, define this notation, fragmented functions from X into, so each individual member in our closure should be fragmented. Fragmented functions. For example, if our original X is compact metrizable space, what is the reformulation? So here we have bare one functions if X is metrizable. And we can replace this concluded by B1 bare one functions. So we will see after our break, we will see some exams. Especially we will touch enveloping sectors. So now I think it's the time to have the break.
Thank you very much. I wanted to recall you that if you want to have water or coffee,